This tutorial will show you how to solve a problem involving a ball falling using energy conservation. We will be finding the potential and kinetic energies and the corresponding velocities of various positions. The problem states a 0.5 kilogram basketball is dropped from a height of 4 meters above the floor. We would like to determine the velocity of the ball halfway to the floor and just before it hits the floor. Since this problem has two parts, let's look at each part separately. In part A, we want to find the velocity halfway to the floor. We're given the mass of the basketball. We also can assume we're on the Earth, so we'll use a gravitational constant of 10 newtons per kilogram. We're given the initial height of the ball as 4 meters. Call that h top. And since it's asking for the velocity halfway to the floor, if we use the floor as a reference point for a zero height, we can assume that the height of the ball halfway to the floor is 2 meters. Call that HA. Now, we can also assume that air resistance is very, very small, so we don't have to worry about it. And if there's no other outside forces acting on our basketball, we can assume that mechanical energy is conserved throughout the entire path the ball is falling. So I'm going to set up a table to help me organize my thoughts. Doing any energy conservation problem, it's always a good idea to break your problem into states, because the idea of energy conservation says that the total energy at each state is going to be identical to the total energy at any other state. So our two states here are at the top and halfway to the ground. Now let's see what types of energies we know about each state. We know that there could be either potential or kinetic energies at different states. So at the top, the potential energy. We also have the definitions of kinetic and potential energy. That kinetic energy is equal to 1/2 mv squared, and potential gravitational energy is equal to m times g times h. So at the top of our path, we can find the potential energy by the mass of the object times the gravitational constant times the height of the object at the top. We know all three of these, so this is just going to be 1/2 times 10 times 4, which equals 20 joules. Halfway to the floor, we can also find the potential energy. It's also going to be found using the same equation. The only difference is we're going to use the height halfway to the floor. So this is going to be m times g times h halfway to the ground, or what we called HA. This is going to be 1/2 times 10 times 2, which is 10 joules. Now at the top, even though it's a tiny bit hidden, we can find the kinetic energy. This problem states the basketball is dropped. Well, the word drop means that the velocity at the top equals 0. And if the velocity is 0, since the kinetic energy depends on the velocity squared, the kinetic energy is also 0. We don't know the kinetic energy halfway to the ground, so we'll leave that blank for now. Now, using the law of conservation energy, we can sum up the energies at each state and set them equal to each other. So in state 1, the total energy is going to be 20 joules plus 0, which gives us a total of 20 joules. And if energy is conserved, this total has to be the same at state 2, also going to be 20 joules. Now here comes the beauty of conservation energy. If the total has to be 20 joules, and 10 joules of it comes from the potential energy at that point, the other 10 joules must come in the form of kinetic energy. So we now know the kinetic energy of our object. The last step is to find the velocity of the object. We can do that by using the definition of kinetic energy. We can set the kinetic energy at state 2 equal to 1/2 m, the velocity at state 2 squared. Plug in some numbers. We have 1/2 times another 1/2 times velocity at a squared equals 10. Do a little bit of math. We have the velocity at a squared equals 40, and the velocity at a is approximately 6.3 meters per second. Now, part B, we can use the exact same ideas. Our state 1 in part B is exactly the same as it was in part A. We can start from the top because energy is conserved, so we have the same amount of potential in the beginning. We have the same amount of kinetic in the beginning, which means we have the same amount of total energy, which means we have the same amount of total energy right before the ball gets to the floor. The only difference is state 2 is a different state. We can use the same ideas. We can say that the potential energy at state 2 is equal to the mass times g times the height at state 2, which we called HB. And this equals 1/2 times 10 times 0, which means we have no potential energy at the ground, which we could have guessed in the beginning anyways, because we can see the object has no height, which tells us that all the mechanical energy of this system at the ground state must be in the form of kinetic energy. And if the total energy is 20 joules, the kinetic energy must be 20 joules. And we use the same process. We can set the kinetic energy equal to 1/2 mv squared, like we did in part A, plug in our numbers, do a little bit of algebra, and we get that the velocity squared at the ground state equals 80. So the velocity at the ground state is equal to approximately 8.9 meters per second. Now this technique is called using conservation tables because we set up a table structure that combines the energies at each state, and we use the idea that the total energy is consistent and kind of keep moving that total energy down and down and down, and the sum is always going to be the same. Now if you're more comfortable with equations, you might prefer a purely mathematical equation way of solving this. So let's go through the same two problems using pure mathematical equation. Now if we go back to part A, we can make the same assumptions. We still know the mass of the object, we still know the gravitational constant, and we still have the ideas of the definitions of potential and kinetic energies, and we know the heights of the object at our different points. So we can write the idea of conservation of energy as an equation, and we can say that the sum of the energies at each state are equal to the sum of the energies at any other state. So in our case, for part A, we have the potential energy at the top plus the kinetic energy at the top is equal to the potential at point A plus the kinetic at point A. Now again, because of the wording of this problem, the word drop tells us there is no kinetic energy at the top, so this is going to go to 0. And we can now substitute in our definitions of potential and kinetic energy into our conservation equation, and then do a little algebra and try to solve this. Potential energy at the top becomes mgh at the top. This is equal to mgh at point A plus 1/2 mv at point A squared. Now using the equation technique also has some advantages. It's a little more abstract, but you might notice now that one thing that happens is all the masses drop out. There's a mass in each part of the equation, so we can divide the whole equation by m, and the mass goes away of our mathematical solution. We're looking for the velocity at A, so we can bring gha to the other side. We can then multiply both sides by 2, and I'm going to pull out g as well, so we get 2g h at the top minus h at point A is equal to the velocity of point A squared. We can now put in some numbers into this. 2 times 10 times 4 minus 2 equals the velocity at point A squared. This gives us 40 equals the velocity at A squared. And just like we did in part A using the table technique, we get the velocity at A is approximately equal to about 6.3 meters per second. This is just a different way of doing the exact same problem. Both solutions are equally valid. It's just a preference on mathematically where you are and what makes you more comfortable solving these problems. Now if we look at part, we got potential at the top plus kinetic at the top equals potential at the bottom, or point B, plus kinetic at point B. Again, the kinetic energy at the top goes to 0 because it's dropped from rest. And at the ground, we have no height, so the potential at the ground also is going to go to 0. So our equation turns into mgh at the top equals 1/2 m v at the bottom squared. The masses again drop out. We can multiply both sides by 2, take the square root of both sides, and we get the square root of 2 times g times h at the top equals our velocity at the bottom. Plugging in numbers, square root of 2 times 10 times 4 equals velocity at the bottom. Well, 2 times 10 times 4 is 80. Again, we get the square root of 80, and our velocity at the bottom is equal to about 8.9 meters per second. The exact same answer we got using a table technique. So there are two different ways of solving a simple energy conservation problem, and although this is a very simple problem, the techniques you can use can be used to any type of energy conservation problem.